right in.
All right there, very good, Marissa. If you'll get our slideshow started while I'm kind of introducing myself here. We're doing this, obviously, we are broadcasting live, so the chances are there's some other people that are watching right now that aren't actually part of the Hangout. So, Miss Veronica, you're not the only one here, I'm certain of. The reason we put this together, we've done a couple of these Hangouts with some students. We're trying to address what the local education community is required to teach as far as weather to the students. This going along with the TEAC requirements. And we've taught some of the students, and it came to our attention that a lot of the teachers themselves said, you know, it wouldn't hurt if maybe I had a little better understanding myself of some of these principles so that I can communicate them to the students as we go through that. So that's more or less how this particular teacher's hangout came to be. So, Miss Marissa, if you'll switch your slides for us, because I can still see you on the screen there, we'll go ahead and get started. I think we only have about 30 minutes officially, although we can certainly stick around a little longer and take some questions once we're said and done. Our time limit's wide open today. We're trying to work this around the teachers that are out there. So as soon as Marissa gets our slides up.
Jason, can you, Jason, okay?
All right, I think we're ready to go. Oops, I lost them, Miss Marissa. You had them up, and I came back.
Kicking me out of there. Give me a second.
If it becomes too much of an issue, I can try to present them on my side here.
Yeah, I'm screen sharing, but of course. Nope. Give me 1 second. I'm gonna try it again.
Okay.
You see him there?
I know I've got a black screen right now.
I'm going to hit present.
You know, you are breaking up a little on me. I'm afraid you may have some bandwidth issues going there. So to kind of keep us rolling, I'm going to see if maybe I can go ahead and share my screen until I see yours come up. Wait a minute. Guess what? Oops.
Okay.
It was there and then kind of disappeared on
Up too soon.
As you can tell, Miss Veronica, we out technical-wise on this end. Want to be running into is a little bit of a bandwidth issue. I'm working on our higher bird, and what we like to do is we like to have Marissa present the slides from her side so that I can go back and forth and visit with you guys. But what I'm going to end up showing on the road, and I'm just going to put my slides up for you, and when I put my beautiful face, but it's probably a much better thing. We'll get higher ratings once it all comes out. So let me go ahead and see if I can share my screen with you, and we'll go ahead and cover some of these basics today. All right, so, you know, as soon as I did that, I think I see Marissa's screen. Marissa, is that you? Can you see the slides? Nope, can't here. I think this is going to work a little better. So, all that said, 5 minutes into this thing, we're at the video. Welcome again. This is really for the teachers. I'm Jason Laney. I'm one of the meteorologists here. Marissa Pazos, one of the meteorologists, and Tim Bryce, which most of you folks have already met along the way. One of the things that we like to emphasize when it comes to the actual idea of weather is the fact that the sun drives it all. Now, I know you're probably thinking, yeah, obviously the sun has something to do with weather because the sun determines how hot it's going to get, and obviously in days the sun doesn't shine, it gets a little colder. Well, it is so much more than that, believe it or not. It's actually the interactions between the sun and the earth that are really going to drive a lot of what's going on. So let me bring up 1 second there. If I could get you guys to kind of mute your mic for me, Marissa. Hello, Marissa. Marissa and Tim, if I could get you to mute your mic for me.
Sorry, Jason. I'm muting the mic now.
All right, very good. All right, so we're back to this. One of the key concepts that a lot of people don't understand is the fact that, believe it or not, the sun really does not heat the air. The type of radiation that comes from the sun, actually the sun gives every bit of radiation possible in the spectrum, but the majority of solar radiation falls in what we call shortwave radiation. And that incoming shortwave radiation, for the most part, just passes through our atmosphere just like light passes through a glass window. So we like to say that the sun does not heat the air. Instead, what happens is the sun's energy passes right through our atmosphere for the most part and gets absorbed at the Earth's surface. So the sun actually heats the Earth. It's the Earth that literally turns around and heats the air, and that's why our heat source is from the bottom up. If you've ever been up on top of a mountain or been flying up high, you notice that the closer you get to the ground, the warmer it is, and then the higher you go up into the sky, well, obviously it gets cooler and eventually it gets rather cold up there. That's because what happens is the Earth absorbs the incoming solar radiation and turns it into what we call long-wave terrestrial radiation. That if you hold your hand close to a fire, you can feel the heat radiating off of it. That's exactly what the surface of the Earth does. So remember, the sun heats the Earth. It doesn't heat the air. It's the Earth that heats the air. But remember, we have these interactions coming from the sun to the Earth. The problem is the Earth does not heat evenly. Some parts of the Earth get hotter. So consequently, the air above that part of the Earth is going to get hotter as well. And what determines how hot the Earth is going to get is basically the angle of the incoming radiation. You see, the sun is much, much larger than the Earth. As a matter of fact, it is so much larger that incoming solar radiation, the rays of sunlight that come in, basically come in a parallel type form. So that means that the sun rays that are coming in right over the equator are going to be more vertical, basically coming in at a 90-degree angle, whereas you get up towards the poles, be it in the northern hemisphere or the southern hemisphere, it's going to come in at a much lower angle. And we like to say that sun angle is the main determining factor of how much radiation is being absorbed. So if you're right here on a case like this one, with the sun angle at 90 degrees over the equator, it's going to receive the most energy. That area is going to get hottest. You get up there towards the Arctic Circle or down near the Antarctic Circle, notice the difference in sun angle. It's not 90 degrees. It's at a very small 23.5 degree angle. And that means you're getting just a fraction of the radiant energy coming from the sun. So less radiant energy, less warming, and you're going to be cooler. So the fact that the Earth is round is one of the reasons that the Earth heats differently. Another thing is the Earth is on that axis. That axis is actually tilted. And the tilt on the Earth's axis is responsible for our seasons, believe it or not. Notice in this particular case, because the Earth is tilted towards the sun, those sun angles that were once right over the equator, now those most direct sun angles are right on top of the Tropic of Cancer. That's 23.5 degrees north latitude. And what happens here, this means our days are longer in the northern hemisphere, the sun angle is higher, and consequently our temperatures are going to get warmer. But what happens if the opposite turns true? And the sun is actually, or the Earth is actually tilted away from the direct radiation of the sun. Well, the Earth itself is not tilted away, just our part of it in the northern hemisphere. That's why when it's winter time in the northern hemisphere, it's summer down south. Notice the direct sun angles now. They're over the Tropic of Capricorn. Now, what a lot of people think is that this Earth's tilt on its axis kind of wobbles back and forth like a top. That is completely not true. The Earth's inclination on its axis stays the same, but what happens is you go from winter, where the northern hemisphere is tilted away from the Earth, and as the Earth begins to revolve around the sun, once you reach springtime, the direct radiation's directly over the equator. Then as the Earth continues its path around the sun, we reach the first day of summer, when the sun's rays are directly over the northern hemisphere. Tack on about 3 more months, we get to fall, the sun's rays are directly over the equator again, and the cycle goes over and over. So not only is it because the Earth is round that we get uneven heating of the surface of the Earth, we get uneven heating throughout the seasons as well because of the way that the Earth is tilted on its axis and the path that it makes around the sun. So imagine this, you've got the sun beating down on the equator. Does that mean every location at the equator is going to have the same temperature? Absolutely not. Because the Earth is not made of the same surfaces. Some areas have more water, such as the oceans and the seas. Other areas have more land mass. And what we find is that land actually gets hotter than water does. If you've ever been near a swimming pool, or near the beach for that matter, you can walk on the sand and your feet burn when you walk across the sand. That's because the land gets hot. But the same amount of solar radiation is hitting the nearby water, but as you dip your toes on into the ocean there, it's much cooler, isn't it? So land is going to heat differently than water is. Land also in the wintertime gets colder than the water. That's why it's so frigid over the continents, but the oceans have not frozen yet. So we've got all these different things to take into account. You've got the curvature of the earth. You've got the change of seasons. You've got land heating differently than water. So what does all this uneven heating do? Well, believe it or not, the uneven heating causes uneven pressure distributions. And this is one of the things that you teach your students about, high pressure and low pressure. If it weren't for the fact that this earth heated differently, we wouldn't have differences in pressure. And the differences in pressure eventually lead to differences in wind. So why is pressure important? I like to say that pressure is important because pressure creates wind. We all know that wind is really nothing more than moving air, right? Well, what causes the air to move? Well, air moves from area of high pressure to low pressure. If you think of high pressure as being a large hill and low pressure as being a deep valley, and you put a marble on top of that hill, you know what's going to happen to that marble up here on top of the H hill? Well, it's going to roll downhill towards the lower area. And that is precisely what air does. So the sun heats the earth differently. The earth ends up with different pressure distributions. And now with heating, we've created things known as wind. So when we teach students about high pressure and low pressure, we like to teach it in this sense. High pressure, basically air is sinking, and when it reaches out, moves away from high pressure. Low pressure, on the other hand, the air actually comes together and converges. When air comes together, it can't pass through itself, so it's forced upward. And rising air currents create what you see here, the clouds. So a lot of people look at this and say, okay, high pressure means we're going to have sunny weather, and low pressure means we're going to have cloudy and lousy weather. Most of the time, there are always exceptions to every rule. But to keep it simple for you, we like to say that high pressure stands for happy weather. That's what the H is all about. So when you have high pressure, generally you have clear skies because the air is sinking. And remember, the colder areas were the areas that we had higher pressure. Warmer areas were areas that had lower pressure. And because the air is sinking and slowly leaving the area nice and calm, we also end up with dry weather temperatures, but then of course a bit colder out there as well. So all of this kind of goes together into setting up what high pressure stands for. Now, Marissa, I've given you control of the slides again so that I can come back to me and maybe do some demonstrations here. So if we'll move ahead, we'll see what happens in low pressure. Obviously, cold air tends to form areas of high pressure. Consequently, areas that warm up more on the Earth's surface create areas of low pressure. And we like to say that low pressure stands for lousy weather, because when that air rises, the clouds form. You get cloudy skies, you get windy conditions. And many times those clouds produce rain and or snow, so you get wet weather, and it can also be followed by cold weather as well. So that's the general layout of high and low pressure out there. So if you want to take a look at exactly what's going on, put all of this together. And most students have seen weather maps that, oh my goodness, Miss Marissa, we've lost you again. I think I'm going to have to go back to my slide. The basic weather map looks like this. Notice you've got your area of low pressure over the Texas Panhandle. That's where the Earth was heating up. You've got your area of high pressure back over New Mexico where the Earth is cooling down. And separating those two is this thing that's a blue line with triangles. That's a front. And students are also taught about fronts with your classes. So what exactly is a front? Well, I like to think of it as the front side of an area of air. In this case, the one that's blue is the front side of cold air. Notice the cold air behind it. And these little points on the front indicate the direction that cold air is moving. The red line that you're looking at with the little half circles, that's a warm front. And if you look at how it's drawn on this map, that's literally the front side of the warmer air. Now, warm fronts and cold fronts tend to move in tandem many times across the country. But one thing that we know is that cold fronts tend to move faster than warm fronts do. And as a result, they create a much sharper boundary. And as they move rapidly in that sharp boundary, a lot of times it takes warm and moist air and forces them up. And cold fronts tend to produce violent weather, or the thunderstorms that we see. Now with warm fronts, a lot of times we will see clouds and we will also see some showers, but in many cases these showers form because of a gentle glide of the air moving up. So what happens ahead of a warm front, you get a cold rain. Ahead of a cold front, you usually get a strong and violent thunderstorm. So cold fronts, because they move faster, because the cold air is more dense, tend to produce more violent weather, whereas warm fronts tend to produce generally cool, rainy conditions followed by warmer conditions there. So that's the idea behind fronts. But you notice the fronts were associated with the pressure. The pressure was associated with uneven heating of the earth. So here's a classic example of what happens as a front moves through. Notice the cold front. That's the front side of colder air. Now in front of the front, the air's nice and warm here. Temperatures 70s and 80s. This is Monday. Take a look at what happens on Tuesday. Now, Texas is a big state, so it takes weather systems a while to move across it. But on Tuesday, the front has moved halfway through the state. And what happens behind the cold front? Well, obviously, temperatures start to get colder. And by Wednesday, when the front has cleared the entire state, temperatures are much colder across the entire state. But not only do cold fronts bring colder weather, the cold front also created that lift of air ahead of it that created the clouds and the showers and the storms. So on Monday, the area where the front was located, just entering West Texas, is where our storms were. By Tuesday, as the front had moved across the middle part of the state, the storms had moved eastwards to about Dallas and San Antonio. But back in El Paso and up in Amarillo, the skies were clearing. It was cooler, but it was clearing. And by Wednesday, that system had kind of moved on away. So that's kind of the idea of cold fronts and warm fronts. But really, fronts and pressures work together on our weather. But it's real easy to remember that cold fronts are the one that create the more exciting weather out there. So let's see, what's coming up next after front is something that you guys have to teach, and this is something that just about every elementary school student knows in one form or another, and that is the water cycle. They can sing songs about it, and I once knew that song, but I've forgotten all the words now, so I won't torture you with that. But this is something that you may not have realized, and even if you do, you didn't realize it was such an important fact. I like to say that water is a super amazing molecule because water, it is the only substance that exists in all three physical states. And of course we know what the three physical states are. They're solid, liquid, and gas. Solid water we call ice. Liquid water, we call it water. And the gas is what we call water vapor. But it's the only one that exists at the temperature and pressure that we have on Earth. It exists naturally, and that's what allows the water cycle to happen. And we all know what the water cycle is. It's that constant movement of water between the Earth's surface and back into the atmosphere. There's plenty of water on the surface of the Earth. As a matter of fact, most of the Earth's surface is covered by water. There's more ocean than there is land mass out there. And as the sun beats down on these oceans and on the lakes and the rivers and the streams, that water tends to evaporate and head into the air. Also, the plants tend to sweat. We talk about sweating as perspiration on human beings, but when the plants sweat, we call it transpiration. And that is a big source of removing moisture from down in the ground where the roots are and releasing that moisture into the atmosphere. So with evaporation from the oceans and transpirations from the plants, we put a lot of moisture in the air. On any given day, there's a tremendous amount of moisture there. But remember what happened to the temperature when you went higher up because the earth the heat was a heat source for the land. Down near the land, it was nice and warm. The higher up you got, it got colder. Well, it turns out that cold air can. So what happens is the moisture begins to condense out. And eventually those water droplets get together and fall as rain or snow, where they run off and get into the ground and the oceans. And it just goes over and over again. But one thing that you'd like to point out to your students is the fact that water is the only substance that can exist as solid, liquid, or gas naturally in our atmosphere and on our Earth. That's kind of a cool thing to know. And you got a little preview of what we're going to talk about next, and that, of course, is the idea of hurricanes. Now, students get hurricanes and tornadoes confused all the time because they're both intense areas of low pressure. I will tell you this, that tornadoes tend to be much smaller. They're associated with one storm. One thundercloud will produce a tornado. Hurricanes, on the other hand, that is a conglomeration of many storms all coming together. And I call the hurricane the greatest storm on Earth because it covers more territory and it produces a tremendous amount of energy. So let's take a closer look at what's going on with hurricanes. First of all, what do you call a hurricane? Well, we call a hurricane because that's what we've heard all of our lives. However, if we lived along the Indian Ocean, chances are when one of these things came ashore, the folks on the news would be calling them a cyclone. And a cyclone is something that we use here in the United States for an area of low pressure. You may even remember from The Wizard of Oz, it was a cyclone that picked up Dorothy's house and deposited on top of the Wicked Witch of the East. Well, cyclone is just an area of low pressure. And that's exactly what a hurricane is. It's a huge area of low pressure. Out off the coast of Japan in the Western Pacific, they call these things typhoons. And one of our favorites is down in Australia. You know, they do everything a little different down in the land down under. They call them Willy Willies. Willy, that's what they call them. All right, let's go ahead before I get into trouble here. I know. Let's talk about what a hurricane needs. I talked about a hurricane being an area of low pressure. Now, we had low pressure on our weather map. Remember, cold fronts and warm fronts attached to them. But these low pressure systems on the weather map in the United States are nowhere as intense, nowhere near as strong or deep as the ones that form out over the oceans. And the ocean is the key. For a hurricane to form, a hurricane needs one very important ingredient, and that is warm ocean waters. Waters that are 80 degrees Fahrenheit. You know what's going to happen with warm water? Warm water is going to be a source of a lot of evaporation. So right above the surface of that warm ocean water, you're going to end up with a lot of warm, humid air. And as that warm, humid air comes together, remember low pressure, the air converged and then was rising. Well, those rising currents create these towering thunderstorms all the way around the center of that low pressure system. And as that air rises, it begins to get deposited aloft. And usually the winds in the upper atmosphere that push the storm along, they're pretty light. Hurricanes move rather slowly out of the ocean, and they could spend quite a bit of time in one location. Consequently, they can do a lot of damage. So let's take a closer look at the anatomy of this particular hurricane. We talked about the fact that it has a center, and the center of the storm, of course, is where the low pressure is. Another name for the center of the storm is the eye of the hurricane. And right beside the eye is where you find the most violent weather. That's the eye wall. That's that towering area of thunderstorms right near the center of the storm. And then there are other bands of thunderstorms further away from the storm that actually start to impact an area before the center ever gets there. We call those the spiral rain bands. So a little closer look at these will kind of goes on each one. As far as the eye of the hurricane is concerned, that's the very center of the storm. But believe it or not, the winds inside the eye of a hurricane are light. And this raises a lot of eyebrows, especially when you tell this to the children. You tell them, hey, this is the biggest storm, the greatest storm on Earth. But hey, right in the very middle of it, there's nothing going on. The storm has pretty much so light winds on it. So we'll talk about why here in a moment. This is where the pressure is the lowest, but sometimes not only are the winds the lightest, sometimes the sun actually peeks through in the eye. If you've seen it on the hurricane, there's that big opening that takes place right there in the middle. But right around the edge of the eye is where the worst of the storm exists. That's where the strongest winds are, the heaviest rain, the strongest tidal waves that come ashore, called a storm surge. That's in the eye wall. That is the most damaging and the most deadly part of a hurricane. So unfortunately, the best part of the hurricane, as far as conditions are concerned, the center, you have to go through the worst of the storm to get there. And unfortunately, the worst of the storm comes again on the backside. But before any of that can reach you, generally an area is lashed out with several bands of rain, and heavy rains at that. And sometimes these bands of rain can produce tornadoes. So a hurricane can actually spawn a tornado before it's said and done. So hurricanes are kind of interesting things there that we has. Now, I told you that in low pressure, now remember in low pressure the air is converging. So you've got air coming from this direction, air coming from this direction. They meet, and when they meet, they have nowhere to go but when they bump together to be forced upwards. It's a little different in a hurricane. Remember, a hurricane is much larger. Actually, before the winds ever reach the center, they start getting directed upwards. And students and teachers alike want to know, why is that? Well, there's actually a pretty simple reason for that, but it may not sound so simple. Have you ever heard of this thing called the Coriolis force? That's an apparent deflection to the right of the movement of a free-flowing object in the northern hemisphere. Okay, forget that definition. I don't even want you to have to tell your fifth graders about it because that's way too much. But for your purposes as the teacher, basically what happens, notice these red arrows around the low. Notice that they're actually running into each other because they're curving in. They're not coming in at a straight line. They're coming in as a curve. And notice they bump into each other before they ever make it to the center of the low. That bumping together is where the convergence happens. So on the right-hand side of this diagram, you see that the convergence leads to the rising air on either side of the center. That's where you get that eye wall and the worst weather and the strongest storms. And consequently, as the air rises and pushes out, some of it pushes together above it and begins to sink. So not only is the eye the calmest part of the storm, believe it or not, Coriolis force. This doesn't show up on the smaller low-pressure systems that move across the United States in the mid-latitudes. This happens with the largest of low-pressure systems. Remember what I called a hurricane? I called a hurricane the greatest storm on Earth. If Barnum and Bailey can be the greatest show on Earth, we can definitely call this one the greatest storm on Earth. So there's your idea with hurricanes. And one of the last topics that needs to be covered when you cover your classes is going to be that of weather and climate. Now, weather and climate, a lot of people get these two confused all the time. They say, aren't they the same thing? Well, honestly, they're not. Weather actually is defined, and it's not defined this way on this slide for you, but it is defined as the state of the atmosphere at any given place at any given time. That's going to be our textbook definition. But to make it simple, really, weather is short-term, based minutes to maybe days, changes or variations in the atmosphere. And when we talk about the atmosphere, I'm talking about just that. I'm talking about the air around us. What do we talk about when we talk about weather in the cold? Those short-term changes are weather. Right now, outside, it's a mild day. That's weather. That's right here. That's right now. There was a guy named Jesus Jones a long time ago that sang a song in the 80s, right here, right now, or something like that. He was singing about the weather. Nobody knew that, but he was talking about the weather. And we talk about it in the elements of weather, and that's temperature and humidity and wind and pressure. Well, those same things can also be classified over long term, basically in aggregate. Climate, textbook-wise, is called the sum total of all weather. It includes averages. A lot of people think climate's just the average weather, and it is. But climate also includes extremes. When you talk about a climate of a place, you can say, okay, in El Paso, Texas, in January, average temperature's probably about 50 degrees. It's kind of cool. But sometimes in January, it can get up to 80 degrees. That's an extreme. That's climate. That's history, basically. And sometimes in January, it can get really cold, maybe 10 degrees. That's an extreme. So when we talk about climate, we're talking about a generalization of the weather in a given place, whereas weather is exactly what is happening at that place at that time. Let's move on to the next slide and see if we can clarify this just a little bit more for the folks out there that have to teach this particular idea. Now, when we talk about weather and climate, we've given you the textbook definitions, but it's real easy to remember this. Weather happens at a particular time and place. Weather's happening in our backyard. The weather at your school may be different than the weather at your house. We noticed that last week when the snow came in. At some people's houses in El Paso, they got a lot of snow. However, in other people's houses and other schools, the snow never piled up at all. So weather happens at a specific place, but climate's generalization for larger areas. So the way we like to say this, is it news or is it history? If it's news, something that's breaking right now, chances are it's weather. But if you're talking about a generalization or the history or what happened at some time in the past, you're probably talking about climate there. So you can think of it one final way. Climate's what you expect, but weather's what you get. You were probably expecting a presentation much nicer than this one. That would have been climate. You got me instead, so I'm going to represent weather, and that's why they call me a weatherman when it's all said and done. So to kind of sum it all up, we talked about the sun. The sun drives the heating of the earth, which drives the heating of the air. Once the air is warmed up, it creates areas of high pressure and low pressure. That creates the moving air that we call wind, global circulations of the oceans. The oceans heat up differently than the land does. The oceans have all that water that evaporates into the air. That creates the water cycle. All of these things you're going to talk about. You're going to talk about high and low pressure when you teach your students. You're going to talk about the water cycle. You're going to talk about wind. But remember the uneven, all of this action that goes on. And you're going to get into a section talking about hurricanes, and hopefully you have a little better idea of what goes on with a hurricane as far as its structure, where the worst of the hurricane is, why the center of the hurricane is not as strong as the area right around it, but it's still the lowest pressure of the storm, and finally differentiating a little bit between weather and climate. Now, I will tell you, I taught this class as a basic weather and climate class at a university in California for 8 years. And most of my students at night were teachers just like yourself who came in because of their continuing education and they wanted to get a little better handle on what was going on. So basically, I have given you an entire semester in about 25 minutes there. And I feel like that's a bit of an injustice for our teachers because there's so much more that you need to know. But that's why we have this last slide available to you, and that's our email address. It's Tim, who is one of our lead forecasters here. Marissa and myself, we're actually classified as interns, but that just means we get to do more work than Tim does, so don't worry about that. And we invite you to send us some emails if you have any questions. You can also contact us. We like to be able to do this because this is our chance to kind of get to know you, the people of our community, and help you with what we specialize in. We understand that you're a jack of all trades, and you probably know a lot more about many things than we do. But knowing that we are supposed to be the experts on weather, and we like to share that knowledge with people as much as we can, we want to take this opportunity to share with you. So if we had 5 or 6 teachers in here, I'd give 5 or 6 teachers the chance to answer questions. Problem is, most of them are watching silently on YouTube right now, so they don't get to talk to us, but hopefully they'll send us some emails. But Miss Veronica, I know that you don't have a microphone there, but you do have chat, and Miss Marissa can see you in the chat, can't you? And
yes,
we want
I
to make
can.
sure
And we are typing back and forth.
Okay. Oh, you guys have been typing all this time? See, I didn't know. I was lost in my own world there. At any rate, if you have any questions you'd like to see, based on what you just heard there, we'll see if maybe we can straighten those out for you in the short amount of time we have left. I haven't seen the chat there, but looks like she has asked a couple of questions.
Veronica, do you have any questions? You can just type them to me. I'm going to send you our email addresses through chat so that, did you get those email addresses written down? Do you have any more questions? And I know you have Tim Bryce's, so you can also, okay, perfect. You can also just email him if you have anything, but we'll try and get you these slides. That's a good idea in the next couple of days, for sure. I guess, Veronica, if you have nothing left, we will just go ahead and close this up. Thank you, Mr. Jason Laney, for your presentation. Thank you, Veronica, for joining us, and we really appreciated it. And if you have any other questions, just go ahead and email us. Have a good day.